The aim of this video is to learn about solving quadratics by completing the square. Let's have a look at the diagrams we can see. On the left we have something that's not a square. So we have an area which is x on one side going up and down there. You can see that side length x, and we have another one x plus 1 plus 1, so that's x plus 2 by x. So if we write that as x times x plus 2, we can, if we like, we can expand that, and we've got an area of x squared plus 2x. On the right hand side we've got what's called a perfect square, and that's length of x plus 1 by another length of x plus 1 side by side. So that's perfect square because we can write that as x plus 1 all squared, which we've seen in the past. So how do we convert or temporarily make something that's not a square into a square? And it's kind of what we're doing with completing the square. We need to do this algebraically if we're to solve or convert the form of a quadratic that we're given when it's not in that perfect square form. Ideally, it'd be nice if we had something on the left hand side, x squared plus 2x plus something else. That would be good. So maybe something like that using b. Of course we don't have that because we can see it up there, it doesn't have that last term. So what can we do about that? Because it's actually helpful if we do have it in that form that we can factorize. Now before we go any further, we need to recall an identity that you should certainly know by now. The perfect square, it's usually referred to as a plus b, but a plus b all squared, or if it's a minus b, there'll be a minus sign under there, is a squared plus or minus 2ab plus b squared. So it's plus, they're both pluses or they're both minuses, okay? And it's only between the first and the second term that there's a plus or there's a minus. It's always plus between the second and the third terms. That's nothing new, you've seen that in the past. Now let's put underneath here, underneath what we've just written, what we just had up to the left there, we had, if you look to your left, we have x squared plus 2x plus b squared. I'm only looking at the plus situation at the moment. I'll just tidy my x up there for you. It's still not great. So we've got that there, and it's apparent if these two things are the same, then that would mean we could infer a few things from that. So that would mean that a squared is the same as x squared, or equal to, and so a would be the same as x. 2ab would be the same as 2x. Of course 2 is the same as 2, and we said a was the same as x, and we've got 1, still a factor of 1 there, so b would equal 1. So a perfect square, if we put all those together, we could write, instead of a squared plus 2ab plus b squared, we could write it as x squared plus 2x, which is what we had on the diagram over here before, plus 1 would be a perfect square. It would be a squared plus 2ab plus b squared is a plus b all squared, so that would be x, following that same pattern, it'd be x plus 1 all squared. But it is true that we put something in there that wasn't there before. That wasn't there. So what we have to do, we have to compensate for that by subtracting that, and after the x plus 1 all squared, we have to subtract 1 for it to be equal to the same thing. So if we add 1 and take 1, we've still got the same thing. The thing is that by writing that perfect square out, we can factorize it, but we just have to remember to minus a 1 on the outside to compensate for it, and that's called completing the square. And if you saw the diagram before, did you notice that for this shape here, the x plus 1 all squared, which is algebraically written there, alright, the x plus 1 all squared up here, it had a little red square. That's subtracted off, and that's a 1 by 1. So you can see that that's the equivalent to that 1 being taken off, because an area of 1 by 1 is 1. So that's both algebraic and a geometric explanation. Completing the square is useful in a number of ways in maths, and the two main uses I guess we're using it for is to solve as another tool for solving quadratics. We've seen factorization in the quadratic formula, but also when we're looking at putting a quadratic equation or a parabola into what's called turning point form, which we'll learn more about turning points coming up soon in the next video or two, but it's useful for those two things. So it's useful for solving quadratics and converting into what's called turning point form, which is coming up in our course very soon. So they're two reasons. They're not the only two, but they're certainly two emergent reasons. Okay, let's say we've got something I've just added here, x squared minus 2x minus 1. Let's say we've got that. Could we factorize that? Could we come up with, if we want to use the decomposition method for example, could we factorize that and and work out, if that was an equation, let's say, factorize and solve that? Well, we'd have to find two numbers that multiply together to be -1. The same two numbers add together to be -2. So that's not going to work, is it? Because when we multiply two numbers together to be -1, the only combinations are -1 times +1, and that will always equal 0 when we add them together. So it's not going to factorize. But sure, we could use a quadratic formula, but completing the square is another option. So let's see if we can apply that there. Remember, we want the form a squared minus 2ab plus b squared, based on what we saw above there, for the expansion of a perfect square. So if we go with that, that would mean that a squared equals x squared. Okay, you can see that there. And that would mean that -2x equals -2ab, or we could just write 2x equals 2ab. It's clear that 2 equals 2, and from the line above, if a squared equals x squared, that means a equals x, and there's a factor of 1 there, so b equals 1. So what we can do then is complete the square. We've got x squared, that should be an arrow, x squared, we'll give an x squared minus 2x, but we're going to write in +1 now, and that is a perfect square. Of course, the original thing wasn't +1, was it, at all? It was -1. Now we've added 1 instead of taking 1 off, so we've actually got to subtract 2 from there to keep it the same. So that was set equal to 0 because it's an equation. So it's a perfect square. A squared minus 2ab plus b squared is same as a minus b all squared. So it's x minus 1 all squared. But it's also got a -2 there. Now we can solve that. Okay. we can add 2 to both sides. We can take the square root of both sides. Sorry, that's an x minus 1. Now I've taken the square root of the left, I've got to take the square root of the right. Just be careful, there's 2 solutions. Now I've got to add 1 to both sides. So it'd be 1 plus or minus the square root of 2, or you could say plus or minus root 2 plus 1. Doesn't matter which order you go. So there's actually 2 answers there for that. Okay, and you've seen quadratics have 2 answers, but this one here, if you tried to write that as a decimal, you'd only be able to write approximation. That's called the exact. 1 plus or minus root 2 is called the exact value. Okay, but that is a place, it's a real number, and you can plot that on a number line, of course. So another thing to note here is we're moving towards this in our next video, most likely. Another form for a quadratic is what's called turning point form, because a quadratic will typically plot to create what's called a parabola, which is that sort of shape or that sort of shape, which you may have seen in the past. And that form's handy because you can identify the turning point, which will be the ordered pair HK. So the form is a outside of x minus h all squared plus k, and more about that in the next video. But you can see that when you've completed the square, you often get something that's very easy to see that it's in that form. Look at that previous example we just saw. Okay, so let's look at an example and find the turning point. Even though we haven't looked at parabolas properly yet, we will very soon. And let's learn the skill in this video here. And let's look at y equals x squared minus 3x plus 1. Let's complete the square so that we can get it in turning point form and get us ready for our next topic after this. So let's complete the square. So we've got a squared minus 2ab plus b squared is the form we want, and from that x squared equals a squared, or in other words x equals a. 2ab is the same as 3x, so sorry, I'll get the order right. 3x equals 2ab. So that would mean that we look at the line above, x and a are the same thing. We can take them out of consideration here. So b would be 3 on 2. And it'd be handy to know what b squared is. If we look at the form, that would be 9 on 4. 9 quarters. So let's put it in that form. So we've got x squared minus 3x. Let me just scroll up a tiny bit there so we can see it. And x squared minus 3x plus 9 on 4. Now be careful, we originally had 1. Now that's greater than 1. Alright, so how much is it greater than 1 by? Well, 1 is 4 quarters, and that's greater than 1 by 5 quarters, so we're going to have to take 5 quarters off. Subtract 5 quarters to keep it the same value. That part there, however, is a perfect square. We can rewrite that as that's x a minus b all squared, so that'll be in this case x minus 3 on 2 all squared. And of course, to make it true, we need to go minus 5 on 4. And that's a turning point form. Turning point form, and the turning point would be 3 on 2, negative 5 on 4. Because remember, the turning point form is a outside of x minus h all squared plus k. So it's minus plus form. Okay, we've got the minus there, we don't have a plus there, so that makes k negative. So 3 on 2, 5 on 4 would be the turning point.